Thank you. Can everybody hear, or can they hear too much or too little? I mean, we're all right? Okay. Yeah, okay, so the menu is on this board. I think I'll start by talking about elliptic curves, and then quadratic twist families, and then disparity, and then statistics, and then make comments, and that'll be my lecture, okay? All right. I should say that everything I'm talking about is joint work with Carl Rubin and his student Zev Klagsbrun. So let me write that. And the roots of the, what's the problem? Henrik.
Well, I was just reading.
Okay. No, I thought, yeah, you didn't want me to cover it up so fast, maybe. Is that it? There it is. Okay. All right. So the roots of the problem that we're going to talk about starts, at least for us, with a paper of Heath Brown, a famous paper, actually, a pair of them. Where he addresses the question of two Selma ranks and the specific statistics of two Selma ranks of an elliptic curve over Q that has full two torsion, also has complex multiplication, but its claim to specific fame is that it's connected to the congruent, the classical congruent number problem. And it's not just one elliptic curve, it'll be a family of elliptic curves. And here's one way of writing them. Where D ranges through all square-free integers, and we're thinking of the elliptic curve over Q. So this is a family of elliptic curves. It's a quadratic twist family, and we'll describe, I'll use the notation that I like for quadratic twist families in a moment. And the whole point about trying to understand this is to understand how the Mordell-Weil group of these elliptic curves, how that group or its rank varies with D. So we have a function from D to these groups, and the question is, how do they vary? And the way in which Heath Brown attacked the problem was by controlling the study of two Selma ranks, and we'll get to that in a sec. Okay. But for us, we will be working with, first, any elliptic curve. Over any number field. So we could, of course, let me see, how do we do this? We could, of course, take our elliptic curve y squared equals x cubed plus ax plus b. And we will like to twist that elliptic curve by, if you wish, square-free elements. But the way I want to describe it, of course, I could just consider the class of all elliptic curves where I put a d in front there. and regard that as the twist. But we're over a number field K, and I prefer to describe it this way. Well, let me put the D there first. And so I might write it this way for D and K, but the best way to really consider these twists is in terms of quadratic characters. So let me introduce the group of all quadratic characters. That's Hom of the Galois group of K into plus or minus 1. They're Dirichlet characters, if you wish, over K. Of course, it doesn't make use of much of this Galois group since I have a plus or minus 1 there, so it passes through the maximal abelian exponent 2 quotient of GK, and a typical element in this I'll call chi. And there's a natural way of twisting my elliptic curve by this character chi over k. And in this way, we have a nice little family, a quadratic twist family, as a function of chi. So it's a function of the elements in this group. Okay. So what do we want to do about this family? Well, what we'd like to do is study, for example, how the arithmetic function chi goes to the rank of its Mordell-Weil group, how this arithmetic function behaves, of k, thank you. But as I think everybody in this room knows, this is a sort of a somewhat more obstreperous arithmetic invariant than one can really handle with this type of generality. And so one will retreat to a study of what we'll call the two-Selmer rank. And in fact, what I want to deal with is what I'll call the reduced two-Selmer rank. So for any E and any K, I'll be discussing this number. It's a number, the reduced two-Selmer rank of E over K. And all you have to know for the moment, although later we'll have to get into the structure, we might get into the structure of how we deal with this and how we work with this, but all you have to know for the moment is, first, it's an integer. And this integer plays the following role. It's an upper bound for the actual rank of the Mordell-Weil group. Second, it's computable. That is to say, this guy is computable, and this guy has an algorithm which should finitely converge to an actual computation of the rank, but has not been proved to be finitely convergent. And the third thing is that this is not so bad as an upper bound in the sense that the difference between these two numbers is conjecturally even. For that, you need only invoke the two-adic version of the Shefrovich-Tate conjecture. Okay. So I'm back to this function here, but not to the rank, but rather to the upper bound chi to S of E chi k. Now, what I want to do is do statistics for this. And so, therefore, I have to do something about the ordering of chi. How do we order these chi's? Well, there's a very nice ordering in Heath Brown's paper. And I should say also that this issue of two-Selmer rank and orderings, some of the best and most precise results we have are for CM curves. So we have results for that CM curve, and we also have results for the corresponding CM curve where one replaces that x by a 1 due to Stoll and other results over Q for larger collections of elliptic curves with full two-torsion, by the way. There's a beautiful paper of Swinert and Dyer, a 2008 paper, where the complexity of the paper is exactly, it's a complicated paper in a way, but it orders the characters in a very, very strange way. So I'm going to sort of start with a particular ordering of these characters. Namely, I'll define something, I'll call it the absolute value of chi. And the absolute value of chi is the max of the absolute values of the norms down to Q of the places of K dividing the conductor of chi. So you see already that there's something slightly non-orthodox going on. Not much, but something in the sense that one might want to order these chi's by simply their conductor. But I'm ordering them in this way. The advantage here, by the way, is the fact that if I just consider the subgroup, the subset of the group of all characters consisting of all the characters whose absolute value is less than any real number x, so ckx is the set of all characters with absolute value less than or equal to x. That's a subgroup. It's not only a subgroup, it's a finite subgroup. And of course, the union of all of them is ck itself. So I'm going to be dealing with that type of ordering. And I think I've described a lot of the title, elliptic curves, quadratic twist families. And now let me get to disparity. So here's a theorem. The theorem is the following. Suppose I take any elliptic curve over any number field. We'll call it theorem 1. And you form the following ratio. I'll call it the ratio of the number of chi's whose absolute value is less than x, so let's say chi's in ckx, such that this reduced two-Selmer rank over K is odd or even, let's say odd, over the total number stabilizes for large x. So the format of the proof of this is interesting. It's not hard to prove this, but here's the format for the proof. So I'm asking whether something is even or odd and attached to a given character. So I can try to package that by taking C of k, the entire group here. And I consider the set of elements even odd, the two-element set. And I'll let capital F be the set theoretic function, which simply tells us whether, if I twist by chi, my elliptic curve, E, which is fixed, over K, has the property that its reduced Selmer rank is either even or odd. So chi goes to the parity of S of E chi. Okay. Okay, so we want to understand this. So here's what you prove. You prove the following thing, that there exists a group, gamma. So there exists a finite group gamma a set theoretic function, little f, and a homomorphism, H, that factors capital F. Once you've done that, you're done. You're done because, in fact, this ratio will just be the following ratio, the number of elements of gamma in capital gamma, this finite group, such that the f of gamma is odd over the size of gamma. What? Correct, yeah. And you can always make it surjective. You just. And of course, since the CKX's fill out CK, after a while, for a large enough x, the image will be, to this finite group, will be everything, and then you'll get everything. What the gamma is interesting. The gamma is there's nothing ridiculous about this gamma. It's just you take a character and you restrict to a certain finite number of bad primes. That is to say, the gamma will be, if you wish, the product over a finite number of bad primes, I'll call them V bad, of the character group of CKV, where KV is the completion of K at V. And this homomorphism is just the natural homomorphism. And this mapping will be coordinate-wise. That is to say, for each V, there will be a mapping on set theoretic mapping of CKV to even odd, such that this, if I call the even odd plus or minus 1, and think of it as a group, such that the F is the product of the local constituents. But I should tell you two things about the bad set and the mapping F. The bad set is slightly larger than what you think the bad set is, and if I get enough time, I'll give you a sense of what that larger thing might be. Tiny bit larger, not always. And the FVs are simply interesting functions. You might say, well, look, this is a parity issue, so we should be able to express the FVs, which Carl and Zev and I define. We define them purely arithmetically. You should express them in terms of, say, the analytic expressions of ratios of epsilon factors in the L function. L functions are elliptic curves and twist elliptic curves. This should be done, and it's a good PhD thesis project, I think, to do. We've done a bit of it. It's tough. Anyway, we have a definition, and I might get to that later. And so therefore, once you do this, you can, you should give this a name, and perhaps I'll call this number. What should I call it? I'll call it epsilon of E k odd. And if you do the same with even, I'd put epsilon ek even is these ratios, and these will be the parities. Of course, you'd be in equal parity if both of them were a half, but they may be, they may not be. And so it's natural to ask sort of how far away from a half are they? And so let me define the disparity. I'll call it d delta epsilon k to be the absolute value of either of these minus a half. And of course, you get the same number if you put an even there. So this would be the disparity. It's in the range 0.5. And so what is it? So compute. It's computable. Here are some things that sort of follow almost by the easiest of the computations. The first fact is if k has even one real place, at least one real place, the disparity is 0. That is to say, we're in an equiparity, so to speak, an equiparity situation. That is to say, we have as much even as odd. In contrast, if k has no real place, and E is good at all primes above 2, good at 2, I'll say, and semi-stable, you never have delta equals 0. You never have equiparity. So just to give you a sense of what kind of parities or disparities we're going to be faced with, let me give you an example. Oh, you can play with a lot of examples, but here's an example that I think my co-authors love, so I will. You start off with the elliptic curve, which is listed as 50A1 in your tome, which, of course, you remember the equation for, right, John? No. Y squared equals x cubed minus 675x minus 79650. Oh, yeah? Well, you don't believe in the eternality of mathematical objects? You've just conceded everything. Okay. Okay, so that's my elliptic curve. Of course, that's over Q, but I'm going to now move it. Over Q, it'll have equiparity. But I'll now move it to some field. So I'll take a field L. First, I'll take a field L over Q that's of some degree D. And I want it to have good behavior with the primes dividing the discriminant. So I want 2 to split completely. And 5 to be unramified. And then I'll consider the following series of Ks, of fields. I'll call them Kn for n 3, 4, 5, and so on. It's L with 2 to the nth roots of unity adjoined. So I have my elliptic curve, which is E. I'm going to consider it over Kn. And so I can ask, what is the disparity of E over these fields Kn? And the answer is the following. 1/2. 1 minus 2 to the minus 2 to the n minus 1 plus 1 all to the d. So that's a hefty collection of numbers in 0, 1/2. Of course, if I've done it right there, I don't think you'll either. Well, I don't know. Yeah. It's even dense. It's dense. And so disparity is going to be with us for quite a while if we're going to deal with the general issue of quadratic families of elliptic curves over arbitrary fields. I mean, that's the main reason for the example, that you can't ignore these disparities. They're here. Okay. So I think in my initial remarks, I've described much of the title of the talk. I now want to talk about statistics.
Did you say in the example which is bigger, the evens or the odds?
I can switch them. There, yeah. In other words, I could start with, yeah. You mean among all of these? Yeah. That's a good question. It's usually easy, for example, first, the evens or the odds, it doesn't really make sense in the sense that if I start with that curve, we have a polarity here, even odd. Of course, I could twist, make it odd, and I start with a twist of that curve and then make it even. So basically, you're asking me what the parity of that one is.
0.
Right. Okay. Okay. Yeah. Another thing you might say, what I've done is I have hidden the sign of this number, and for good reason, because I didn't want to say what the parity of my starter curve is. If I knew the parity of my starter curve, I would remove the absolute values, and then I'd get a formula with a -1 to the r of the starter curve. So that would be the big difference. Okay? Okay. Okay, now I'm on to statistics. Now, the statistics are rather curiously a Markov process, and so, or guided by a Markov process. And so I'm going to try to describe my Markov process as in Keating's lecture yesterday, where there was this digression about statistical mechanics that we're supposed to go to sleep during that turned out to be the whole point. I'm going to try to do the same, but don't go to sleep. Okay, so I have a line here, and I have stations. So this is the 0th station, this is the 1st station, this is the 2nd station, and so on, you know, all the way. And in each station, I have a heap of sand of different heights. And of course, I'll want the total mass of sand to be finite. I don't care how it is. But the total mass I'll want to be finite. You could even normalize it to be 1 if you want. Probably won't play a role. And now I'm going to consider a certain process which I'll call M for Markov, which redistributes the sand. So what do? The first thing I do is I take all these heaps of sand off their stations. So they're off. 1, 0, 1, 2, 3, 4, 5. But I'll put the even ones to the left. And the odd ones to the right of the line. And now, as Weiho told me I should use colored chalk for this, so I will. I'm going to redistribute these things. Okay, so the pile that was on the 0th station, I'll put them all on the 1st station. So I'll call that 1 over 1. The pile that was on the 1st station, I'll put half and half on the 0th and 2nd station. So I'll call that 1/2, 1/2. The pile, where's my blue chalk? Hey, the pile, here I'll go 3/4 down and 1/4 up. So 3/4, 1/4. And then the 3rd station, 7/8 down, 1/8 up. And you begin to see the pattern. So this would be 15/16. This would be 1/16. Okay, you just keep going. So that's the redistribution M. Now notice that there are various things that you should notice even before we get going about this. The first is, what's happening is the odd stations are being redistributed to the even stations, and the even stations are being redistributed to the odd. For example, if there were no sand at all on the even stations, then after one application of M, there would be no sand at all on the odd stations, but all the sand will be on the even ones. And the other way as well. So we might be also interested in iterating M twice. I'll call it M squared. When we iterate twice, another thing, funny thing happens, which you'll see in a moment. Namely, the odd stations and the even stations don't know each other. They don't even interact. So whatever is happening on the odd side or the even side, well, independent, totally independent. It depends on what sand there is. Okay. So how do you deal with this? Well, of course, the natural thing to do is to pass to a limit. I want a limit, the limiting sand distribution, so to speak. Limiting. But you have to be careful about what you mean by the limiting. I'll still call it sand, why not? Distribution. I can't say take the limit of m to the k, but I can say take the limit of m squared to the k. So I'm taking lim of m to the 2k, as k goes to infinity, and see what happens. You get a distribution of sand. Now, since the odd and the even are playing such different roles, and since I've assumed, let's assume that the total mass is 1, let's introduce the two numbers, epsilon even and epsilon odd, to be the mass that's on the even stations and the mass that's on the odd stations. And of course, their sum is 1 because I've normalized to be 1. Okay. So this is a standard Markov game. And the limiting sand distribution will then produce for each station something, a mass of sand. And the sum of all those masses of sand will still be 1 because we haven't added or contracted or gotten sand in our cuffs while doing it. So, so there's some distribution. And here's the distribution. We'll do what Euler does, namely make a generating function for the distribution. It's not quite the actual distribution, as you'll see, but it'll be close. And it's given by this rather beautiful infinite product. I equals 0 to infinity. 1 plus 2 to the minus I z over 1 plus 2 to the minus I. Okay, you expand this out, and it actually expands out. It turns out that if you do expand this out, the dn's will always be positive numbers. They'll never be 0 or negative or anything. Visibly, what? Oh, the nth coefficient of this generating function, which you get by expanding this guy out, which I will never write. I can write it. I mean, there are formulas, but okay.
So this depends on the beginning.
I haven't given you the actual limiting distribution. The limiting sand distribution will be at the point n, at station n, you will get, and you guessed it, epsilon even times dn, or epsilon odd times dn, depending upon the parity of n. Okay? Now, this is a beautiful structure here. I mean, the minute you see this infinite product, you can't resist playing an enormous number of games with it. So let me play a few while we have it on the board. The first thing is, it's obvious that the sum of the dn's for all n is 1, because you substitute z equals 1 here, and you've got 1. It's also true that the sum for n even and n odd are equidistributed. And ditto for odd. Probably the easiest way to see that is put a -1 in there and play. You'll find that with a -1 for a z, that's 0, and so that will tell us this. Suppose you want to know, well, suppose you want to know the sum of n times dn, which will be actually a bound for the average rank of elliptic curves once we get going. You take the derivative of this guy and you evaluate it 1, and you can do that. Suppose you want to know the average size. The average size, well, you replace z by, the average size, I haven't told you of what, so here we go. Now let me make this apply to reduce to Selma rank. So here's the conjecture. I'll state it as a general conjecture and talk about when and how, in what sense it's proved. So the conjecture is, let E and K be arbitrary, elliptic curve and number field. Let's let epsilon even be what I called epsilon of EK even, and ditto for odd. And then the limit as x goes to infinity of the ratio, the number of elements of chi in CKX, such that the reduced Selma rank of E chi is n over the total number converges and is equal to epsilon. Well, if n is even or odd, depending upon whether n is even or odd, epsilon even or epsilon odd times dn. That's the general conjecture. And in fact, that conjecture is something that's proved for that CM, well, it's no longer there, but the CM elliptic curve that was on that blackboard. And this is an MSRI program, and for a large part of what Zev Klagsburn and Carl Rubin have done, we've done it here, but we have something in the direction of this conjecture in the following sense. There are two shortcomings, so to speak. The first is we only can work, really, given our methods, with elliptic curves such that the Galois representation of GK to GL2 F2, which is the automorphism group of the points of order 2, is full, is surjective. And I might give you a sense of why this helps us enormously. And the other thing is this notion of ordering. We would love to be able to do it with, for example, that ordering, but we can't do it we don't do it with that ordering. We do it with what I'll call a box ordering, a slight modification of this, having to do with successive applications of the effective Chepitarov theorem. in order to give you a sense of what this box ordering is, let me start off by mentioning what I think I swept under the rug before, which is what are the bad primes that we deal with. Here's the point of our method, actually. Our method is simply to take two descent and sort of find what's the minimal amount of structure you need to be able to do two descent and try to control that structure. Well, I think people know that at least to do two descent, you have to have an understanding of the GK action on the points of order 2 of your elliptic curve. And in our case, that simply defines a field extension with Galois group, the symmetric group. I'll call it L and S3. So L is K with the coordinates of the two torsion adjoint. But that's not enough if you're ever going to sort of get any of the results that you really want to get. There's a Heisenberg structure. There's a Heisenberg group of it. This is only a Klein group, after all. It's a Klein 4 group. There's a group of order 8, which I'll call H for Heisenberg, mapping to E2. It's the quaternionic group. Which maps surjectively to E2, and of course the center is the kernel. Okay. Now, once you have this Heisenberg group in mind, it's somehow canonical. It's canonical given an appropriate level structure of the elliptic curve. If you give yourself a PGL2 Z mod 4 level structure, you've got this Heisenberg group. And so therefore, if you think of all elliptic curves as being bundled together by this structure, which is canonical, you get a modular curve, and it's a genus 0 modular curve. So if there's one elliptic curve with such a quaternionic structure, there'll be infinitely many over whatever field you're working. So you're in good shape in trying to understand two descent not only for a single elliptic curve, but for one parameter genus 0 modular family of elliptic curves all at the same time. That's a good thing. The thing about this, it's just, as I say, it's just a group of order 8, but it has a GK action. And this, of course, has a GK action, and the GK actions are compatible. The GK action on plus or minus 1 is trivial, of course. In any case, we can do the long exact sequence for non-abelian cohomology of this action. And so we would take find ourselves with connecting map, I should say, which is not a homomorphism, H1 of K, with whatever field you're dealing with coefficients in E brackets 2. Now, this is, of course, an infinite group. It's always infinite. It's the infinite group within which the two-Selmer group lives by giving local conditions by reduction to the places kv for v running through all the places of k. But h1 of this goes to h2 of this. Now, h2 of this, of k is a number field, this is just the points of order 2 in the Brouwer group of the number field. So for example, if this were, we pass to a local field, h1 of kv, e brackets 2, to h2 of kv plus or minus 1, that is just canonically, as it can only be canonical, plus or minus 1. Well, what shall I call it? I'll call it plus or minus 1. Okay. But this is not a homomorphism. We'll call that Q. We'll call that QV. It's quadratic. And in fact, for every v, this quadratic function, if you wish, this quadratic function, what this quadratic function does is defines, if you don't mind my saying, because these are such small groups, a quadric in the projective space generated the projectivization of that vector space, h1 of kv e2, and it's non-degenerate. So we have a non-degenerate quadric in here. Now, there's a preferred quadratic extension, which I'll call kv unramified, over kv, namely the unique quadratic unramified extension of kv. And h1 of kv, e brackets 2, of course, restricts to the h1 of this field as well. And so there's a kernel. I'll call this the unramified Lagrangian in h1 of kv, e brackets 2. This kernel is of half the degree, by the way, of the degree of this extension, of this vector space. And the Q, the quadratic function, defines a quadratic form on the vector space, as quadratic functions always do. It defines a non-degenerate quadratic form, which is essentially the symmetric bilinear form induced by the Weil pairing. And we'll say that V is good for Q if the unramified Lagrangian is a maximal linear subspace in the quadric determined by Q. If the unramified Lagrangian killed by Q well, QV. Okay. Now think of the situation here. We have a projective space. We have a quadric. We have a smooth quadric on the projective space. We have, for example, the usual situation, which will happen infinitely often, is where this is dimension 4. So our projective space is P3. Our quadric is a quadric surface. A quadric surface is biruled. There are two lines of rulings in a quadric surface, and the unramified Lagrangian is one of them. Now, we're asking that the unramified Lagrangian is in that quadric, which means that each of these two families are defined over F2. So there are 6 possible families. And what happens when you twist, the local conditions will never flit from one of those families to another. They will stay within one of the families of 3. And in particular, if the unramified Lagrangian is killed by QV, all the local conditions will be one of the 3 vector spaces in the case where this is dimension 4 of which represent lines of that family in the quadratic surface. Okay, now I can now tell you what I mean by V bad. V is bad if all the usual if V is one of any of the usual suspects. If V divides 2 times infinity times the conductor of E, and is not good for QV. There's an extra condition, good for QV. So that determines a finite set. That's a finite set, by the way. That determines a finite set of bad primes. And that finite set of bad primes is what rules the entire descent mechanism. If you know what's happening at the finite set of bad primes, you really have complete statistics for the entire descent mechanism. And I can also now tell you what do I mean by box ordering. I write chi, a typical chi, and it will have a conductor. So I'll call the conductor C of chi, C perhaps. And I want to break this conductor as an ideal, as a product of 4 ideals. C bad. That is to say, I take all the primes dividing the conductor that are bad in this sense, times C1, C2, C3. Now, C1 is if in this extension, L equals, I'll call it LV equals E of, KV of points of order 2. Perhaps the easiest way to say, I just want Frobenius. Perhaps I'll do it this way. I'll say if this has a degree. That is, say I want to have the degree of Frobenius at V in the extension generated by points of order 2, and let me just say if the Frobenius of degree Frobenius at V of degree I equals 1, 2, and 3, since the Galois group is a symmetric group of order 3, there are only 2 or 3 possible things. And we break the conductor up into these 4 primes. And now the box has the following requirements. We require that we have a sequence of numbers determined by essentially a successive use of Chebytarov theorem. These numbers grow with x, and I want the places of C1 and the places of C2 to be bounded by the sequential sequence of numbers that grow with x, and I'd want the norm of the absolute value of the norm of C3 to be similarly bounded, but I don't count the places. So that's a rather rough description, but I want to say one thing, that when we do it this way, we have quite a number of average. We force our box to average extraordinarily over the places where Frobenius has order 3. And this turns everything into rather beautiful Chebytarov conditions. If we didn't do that, we would be faced with rather interesting assortments of primes, but we couldn't make statistics with them. I think that's enough of what I want to say about the technical aspects of the proof and how it works. We hope that there's a kind of robustness here. We hope, that is to say, that with better understanding, either we or someone else would be able to somehow replace our box ordering by what I would consider a much more appropriate ordering given by these finite groups. Yeah? Oh, we proved that conjecture for all elliptic curves over all number fields for such that the Galois group maps surjectively to GL2F2, but we order not that way. We order rather with our chi's by, well, to be more precise. I'll define B, J, K of X, the set of all chi's. We have certain growth numbers. I'll call them A1 of X, A2 of X, and so on. Now, these are real valued functions that go to infinity, going to infinity with X. These are the sides of our boxes. And we consider those chi's such that there are at most j places in C1, at most k places in C2. And for these j plus k places, you can order them any way you want. I'll want the, I'll call them V1 up to Vn, where n is less than or equal to j plus k. I'll want the norm of the absolute value of each of these Vi's to be less than or equal to Ai of x. And then as far as C3 goes, I'll just want the norm of C3 to be less than or equal to an plus 1 of x. That's my box. And with this box, and with very specific numbers, they go to infinity. They're inductively defined using Chepatarov, of course. And if you have a if you're willing to use the GRH, you get a fairly good sequence of box sizes, if you wish. And the theorem would be what? N is the number of places in C1 and C2. So n is less than or equal to j plus k because there are at most j places in k in C1 and k places in C2. What? What? They're increasing. They're monotonic. Yeah. What? They're increasing. Yeah. Right. Okay. And now here's the theorem. Maybe I'll write it here. The limit as x, j, and k go to infinity in any way you want, any way, of the ratio, number of chi in the box, b, j, k of x. Such that s of e chi k is equal to n over the number of elements in my box. That limit is equal to epsilon, even or odd, depending upon when n is even or odd, times the dn in that Markov process. That's the theorem. And the theorem is for all E and K subject to surjectivity of GK. Okay. Now, the reason why we need surjectivity is we need these primes of type 3. The primes of type 3 are kind of freebies, and they allow you to average without losing much information. And so our theorem would not work if we didn't have any primes of type 3. Okay. So I guess that's what I wanted to say.